Okay, so thanks for coming back. So the next presentation will be given by Remsing from Rutgers University, and we're talking about surprising effects of vacancies on surface. I'm excited.
Yeah, so first thanks to the organizers for having me here. It's been a great workshop. Learned a lot. I kind of changed the title a little bit. I had some other things based on all the talks this week. I guess that's a good thing about being the last day. You can change your stuff to catch up to what everybody else is doing. So the first part of the talk will be kind of more about surface hydrophobicity, and I'll just get to the main point about the vacancies, and then I'll talk a little bit about polarization forces in confinement that involves water and ions, and I think will be of interest to people who have talked about ions. Before I do any of that, I want to get the acknowledgements out of the way first, so I'll try to be on time. So this is my group as of last summer. There's some people not pictured that need to be added, but we keep the website updated pretty often. The various funding sources. And then different parts of this project were done with different collaborators. So the polarization stuff at the end was done with these people on the left, as well as a larger group of people. I'll mention some work with Hemant Kashyap at IIT Delhi and some of his students, one of which, Harinder, is now a postdoc in my group, which is why he's in a different shape. And then some work on alumina surfaces with Eric Bourget, Enzo Carnevale, and their groups at the Temple University. And I want to just give some idea too of what we do in my group, since I'm meeting many of you for the first time. So in addition to what I'll talk about here, we do a lot of modeling for materials for energy. So things like solid state electrolytes, perovskites, materials for catalysis, and defects, which is our interest in MOS2. We have a big section of the group that works on modeling materials and problems in astrobiology and planetary science, so things like modeling chemistry on the surface of cold worlds and organic minerals or molecular crystals. And then we also do a lot of method development, so we develop things like machine learning techniques for long-range interactions, path integral models for being able to model things like excess electrons in semiconductors and be able to simulating them in complex environments and things like that. But I'm not going to talk about any of this stuff today. I want to talk about things relevant to this workshop. And I'll start by introducing something that's been introduced quite a few times, right? And this is drying in nano-confined liquids. I'll look up here, I guess. It's hard to decide which screen to look at. And the general idea, right, is that confined liquids are different than they are in bulk. And as we've seen throughout the week, right, if you bring two hydrophobic surfaces close enough together, then you will get drying or capillary evaporation between the plates. I'm going to say drying or de-wetting, even though that's maybe not a technically correct term, instead of capillary evaporation, partly because it's just easier to see. And this drying is driven really by hydrophobic solvation of these two plates. And so if we think about the assembly of two hydrophobic objects, we generally think about having these two objects far away. We bring them together and we compute the free energy of bringing these two things together. But you can rewrite this free energy exactly as a difference in the solvation free energies of these two states, right? So you can compute the solvation free energy of these two hydrophobic plates or hydrophobic particles far away and together, and that difference is the free energy of bringing them into close contact. Right? And as Peter mentioned in his talk, the hydration of hydrophobic things depends on their size. And so if you look at the solvation free energy of a hydrophobic particle, right, and for small particles, this scales linearly with the volume of the particle, but for large solvent volumes, this scales with the solute surface area. And we can write the solvation free energy of an ideal hydrophobic particle, so a hard sphere, as a negative log of the probability of finding a cavity in the liquid, the size and shape of that particle. So this is this P of 0 here. And so the 0 refers to the number of waters in that volume. So it's the probability to find the 0 waters in the volume, the size and shape of that particle. And so for small particles, you can kind of insert or find these small cavities kind of readily available in a liquid, but for larger particles, this would correspond to having something like a larger bubble in the fluid. And we can look not just at n equals 0, but we can look at the entire distribution of P of n to get some more physical insights into these processes. I think this is the exact figure Peter showed in his talk. And so for small scale solvation, these small solutes can fit, at least in water, readily within the hydrogen bond network without disturbing it. And as a result, this entire distribution P of n is remarkably Gaussian. And so you can treat this P of n on small length scales as just some Gaussian distribution. And if you have the mean and the variance of the particle numbers, you can get everything you need. In large scales, right, the water hydrogen bonding network can't go around these solutes anymore. You have to break hydrogen bonds. You create an interface, and when you create an interface and you nucleate this liquid vapor-like interface, you have to, this gives a signature in this P of n of these non-Gaussian fat tails at low n, which sort of signifies this vapor nucleation. So this is just for bulk, but then what happens if we start looking at these things near hydrophobic surfaces? And the consequence of this sort of large length scale or the non-Gaussian tails at large length scales is that near a hydrophobic surface, these non-Gaussian tails or these fat tails become even fatter. And so if I had look at these P of n's next to a hydrophilic surface, like this red curve, you can see that the tail is not so fat, but if I make the surface more hydrophobic, this tail in the P of n gets fatter, the P of 0 goes down a lot, and so it's much easier to empty a volume near a hydrophobic surface, near a hydrophilic surface, which makes sense because emptying this volume corresponds to having a hydrophobic or hard solute absorbing to the surface, so it's easier for these things to absorb at a hydrophobic surface than a hydrophilic surface. And so this is sort of the general thermodynamics for one surface. Now let's go to two surfaces. What happens, right? And the thing that happens near two surfaces is that when you have them in close contact, you can have these sort of enhanced density fluctuations, but then they can merge and you can empty the entire region between the two points. And so I'm not going to go too much into this, right? Antonio and then Gonzalo give talks on the beautiful work they're doing on understanding these processes. I'll just highlight, that the general picture, right, is that as you start to empty these volumes near the surfaces, you start to get bubbles forming near these walls, and then they form a plate spanning vapor tube that can then grow, and you get complete drying. I do want to highlight one thing that I think is one system that we've looked at that I think is pretty interesting in this context, based on the fact that line tension has come up a few times. We explored these kind of things in ionic liquids and water and salt electrolytes with Hanad Kashyap's group at IIT Delhi, and it's the same general setup we think about for water intrusion extrusion, except we're going to do it with this lithium TFSI plus water and salt electrolyte. And if we look at the general mechanism of drying between these plates and calculate free energy profiles and all of this stuff, it's essentially the same picture we have for water. So you have these enhanced density fluctuations near the surface. You get these bubbles forming next to each surface as you start to evacuate the space between the plates. They merge into these tubes, the tubes grow, and you get complete extrusion of the liquid. But some interesting things show up if you look at concentration dependence of this drying, and particularly the barriers to intrusion and extrusion with the concentration dependence of these water and salt electrolytes. So as you decrease the concentration, the barrier height decreases. But if you try to write down some macroscopic thermodynamic theory for the barrier heights, which actually fits well if you do this for water, for example, and you compute things like the surface tension and the contact angle from independent methods, independent simulations, what you get is that this macroscopic thermodynamics using the contact angle and the surface tension says that these barriers should increase as you decrease the concentration. Right? So it's completely backwards. And instead, what we find is that if you now include a line tension term and you look at the line tension in these systems, the line tension actually increases with concentration. And this line tension term is what governs that decrease in the barrier to drying with concentration. So we're seeing a pretty significant role for line tension in in these systems. So I think since line tension came up, I just wanted to. All right, but let's get to sort of surfaces that aren't perfect, right? I want to get to thinking about things like vacancies and defects and patterned surfaces. And so everything that we've done that I've talked about so far is for perfect systems, but real systems typically have things like vacancies, interstitials, grain boundaries. Maybe you have electron or holes trapped in these types of defects. And if you want to understand how water interacts with these sort of surfaces in operating conditions, you have to start thinking about how they interact with all of these different types of defects that appear. And in many cases, like catalysis, these defects are actually the active sites, right? So we really need to understand how water is wetting these surfaces. And so again, what we're going to do is map these surfaces looking at density fluctuations, and this is not something new. This goes back a long time, and there's this excellent review article from Shekhar Gardi's group, who's done a lot of work on this stuff that has shown that things like the average density of water next to a surface is not a good indicator of hydrophobicity. You have a very hydrophilic surface with a smaller density than a very hydrophobic surface, for example. But really, it's the fluctuations in the water density that tell you whether or not something is hydrophobic. So how easy it is to create a hydrophobic cavity or drive a hydrophobic molecule to that surface. And we can actually, and this was shown by Amish Patel over 10 years ago, that you can actually show that the emptying of these volume next to surfaces is proportional to the contact angle. So if you use macroscopic thermodynamics, you can say that the difference in creating this bubble at the interface relative to the bulk is equal to the surface area times the surface tension times 1 minus the cosine of the contact angle. And if you plot this, you can see a very good correlation between emptying these volumes on nanometer length scales and the contact angle that you would get macroscopically by putting a droplet on the surface, right? And so we can think of these, P of zeros or the free energy to empty these volumes as sort of a nanoscale analog of the contact angle. And we're going to look at things that characterize this distribution. I want to talk about how we calculate these, since there was a question about this the other day. We use something called indirect umbrella sampling, or INDIS. And the basic idea is that if we're doing molecular dynamics simulations, you want to bias the number of particles in a specific volume, but the number of particles is a discrete variable. You can't, you'll get impulsive forces if you start to take derivatives of a potential that depends on that. So instead, you smooth this end. So if you have a boundary, and I think this was mentioned, instead of having a sharp boundary, you just make it continuous, and you get some continuous variable n tilde, and this n tilde closely follows n. And so you can get your probability distribution P of n by getting the joint distribution of P and n and n tilde, and then integrating over the n tilde. And you can get these P of n's pretty efficiently using enhanced sampling techniques if you can't get them from unbiased simulations. And even if you don't want to do the entire distribution, we've developed a method for computing just certain points in the distribution that follows the distribution exactly. And so instead of applying some kind of umbrella potential or something, you can apply a linear field, just phi times n tilde. You can compute this average n as a function of phi at some particular phi values. If it's a hydrophilic surface, this n as a function of phi is going to be linear. Hydrophobic, you're going to get some sigmoidal curve due to the drying transition. And you can write your probability that you want in terms of the bias probability, subtracting off the bias potential and this free energy term that you get from thermodynamic integration. And if you compare computing these distributions with all the points, which are the lines, versus just points scattered for these different values of phi, you'll get a good idea of the shape of the distribution. So before I get to defects, I want to talk about the surface where we've used this technique to show some differences between nanoscale hydrophobicity or hydrophilicity and macroscopic hydrophobicity. And this was with alpha alumina. And so we looked at two surfaces of alumina, the 112 bar 0 and the 0001. And there's some differences in the aluminol groups that are exposed to the water. Right? So there's 3 types in the 112-bar-0, but only one type of luminol exposed to the water in the 0001 surface. And both in simulations and experiments, water completely wets both of these surfaces. So this was an interesting case where the simulations actually kind of drove the experiments to kind of be a little cleaner, I think. And so here, if you put a droplet of water on either of these luminous surfaces, it rapidly spreads. And if you do the experiments, and you have to make sure these surfaces are very clean, you do a good job of keeping them clean, you find that the surfaces also essentially completely wet. And so we have good agreement between the models and the experiments. And so now we can start looking at these P of N's near these surfaces and comparing to these sort of macroscopic ideas. We can write down thermodynamic expressions for the free energy of creating these cavities in the bulk or at the surface. In the bulk, it just involves the liquid gas or the liquid vapor surface tension. But near the surface, you have three-phase contact lines, so you need all of them. You can write down, rearrange these expressions using Young's equation to get an expression for the contact angle. So the contact angle involves the difference between the free energy to create a cavity at the surface and in the bulk. And if we have a macroscopically wetting surface, right, this would tell you that cosine theta is 1. And so the free energy to create a cavity at the surface should be equal to that in the bulk. And it implies that all completely wetting surfaces would have the same free energy to create a large cavity near the interface, at least on the macro scale. But we're not looking on the macro scale, we're looking in nanoscopic volumes, so things like 1 by 1 by 0.3 cubic nanometer cuboids. And if you look at the free energy as a function of the number of particles, so the negative log of these probability distributions, and you look at their value at 0, so 0 is the free energy to create these cavities, what you see is that they're not equal. Right, so the bulk is actually the lowest free energy to create these cavities, whereas both the luminous surfaces are higher, and the 0001 is the highest surface. And so we're seeing some differences that emerge at the nanoscale. Essentially, right, these surfaces are super hydrophilic, if you want to call them that, on the nanoscale. But as you make these volumes bigger and bigger and bigger, these free energies have to tend to the bulk free energy. There's some differences there. And the differences between the two surfaces just comes from differences in interfacial hydrogen bonding. So there's better hydrogen bonding to the 001 surface because there is only this one type of luminol group, whereas the 112-bar-0 surface has these three different groups, and some of them don't hydrogen bond so well to water. All right. So let's go to defects. So defects, we can't look at one-dimensional plots anymore. We're gonna have to look at two-dimensional plots. And so there's been lots of work already done on mapping pattern surfaces and patchy surfaces, looking at density fluctuations in the two-dimensional plane. And so we're gonna look at plots that sort of look like these things on the right. And the idea that has emerged from all of this work is that if you were to put, let's say, a hydrophilic patch into a hydrophobic surface, that alters the response of water more than if you were going to do the reverse, putting a hydrophobic patch in an otherwise hydrophilic surface. Okay, so there's this sort of asymmetry between hydrophilic and hydrophobic patches. And if we're thinking about things like capillary evaporation, these small hydrophilic groups can do things like hold on to water while everything else has evacuated. And so we're going to look at defects or vacancies in monolayer MOS2, which is a layered, it comes from exfoliating a layered transition metal dicalcogeniide. This interesting 2D material, right, which is kind of, people are interested in, similar to graphene, lots of interesting things happen when you go to a single layer. In this material, for example, in the bulk form, you have an indirect band gap, but when you get down to the monolayer form, you have a direct band gap that's in the solar range. And so there's lots of interest in MOS2 for things like photocatalysis and photovoltaic and other photophysical applications. Skip through that, but I'll just say, in catalysis, there's lots of interest in these materials and these defects, because there's been some recent work that has shown that depending on the state of these defects, whether or not there are things like electron traps, you can have the catalyst switched on and off. And so this is governed not just by things happening within the semiconductor, but also by things that are happening in the liquid. And so the first thing we want to do is understand if we have a vacancy in this system, how does water bind to this vacancy? There's been some experiments and DFT calculations on these things. We want to see if our simple molecular dynamics models can get these things. And so the structure that we get does agree pretty well with experiments, and we can start doing things like computing free energies for water to bind to the surface. And so if we have a perfect surface, we can get a free energy of water absorbing to the surface that looks like this. There's not much going on. It's sort of a not super hydrophobic surface or anything. I think the contact angle is around 90, so it's right at the border. But then if you have a vacancy, you see a well-defined minimum at smaller distances appear in the free energy, meaning that water is sort of binding to this vacancy. And I think we would say that this means that the vacancy is hydrophilic. Water is strongly binding there. I'm not going to talk much about this, but we even have developed ways to simulate things like electron traps at these vacancies. And when you do this, it causes the water to unbind. Happy to talk more about that over the coffee break and lunch if anyone is interested. Well, we want to look at the hydrophobicity of these things. And so my student Josiah said, well, one vacancy is not enough for me. I'm going to start putting in 2 and 3 and 4 and 5. And he really explored a whole bunch of different numbers of vacancies and vacancy configurations. I just want to show a couple highlights here to get the point across. And so here's a system where Josiah has looked at 3 vacancies arranged in this triangle shape with a single sulfur atom between each of the vacancies, right? So you have a little triangle of sulfurs in the middle. And if you look at these density fluctuations, aside from these bright spots, which are the waters that are bound to the vacancies, the water on top of those exhibits larger density fluctuations than anywhere else over the surface. And so we can look at a P of n just for this region in between these vacancies. And we can do this with having no vacancies in the system, a single vacancy where we place this volume next to the vacancy, or 2 vacancies where we place it between the 2 vacancies, or in the center of this triangle. And as you add more vacancies in the system, the P of 0 goes down, right? Meaning that, even though we're adding these sort of hydrophilic sites, these hydrophilic patches that are these vacancies, the region near these hydrophilic patches is becoming more hydrophobic than the rest of the surface, right? Which I think is counterintuitive. That picture of hydrophilic patches make the surface more hydrophilic. And so you can think that maybe this has interesting consequences for things like assembly and maybe some of these patterning walls for the applications that we've discussed here. And what we think is causing this are changes in both the hydrogen bond network and pinning of the interface. So these waters are slightly lower than the rest of the interface, so you have to drag the interface down at these spots. But if you look at the orientations of the bound waters in blue, they're mostly pointing their dipoles up, right? Their OH bonds are up, whereas waters at a hydrophobic surface tend to lie flat or point an OH bond towards the surface. And so you have this sort of reorientation of the hydrogen bond network near these bound molecules, but then that hydrogen bond network has to rearrange again to sort of satisfy the hydrogen bonding with the waters at the hydrophobic part of the surface. So there's this sort of competition and the incommensurate nature of the network. And with the last little bit, I want to talk about some stuff where we found a similar competition that leads to sort of hydrophilic patches behaving differently than they would if the entire surface was covered with those patches. And we found this a while ago in these model silica surfaces where we just have dipoles on the surface. And so we have a plus charge and a minus charge, and we can tune the magnitude and the sign of the dipole with just some coupling parameter. And so we were doing this in the context of trying to map these surfaces, not by using density fluctuations, by looking at sort of macroscopic or coarse-grained charge distributions of water. So essentially trying to look at the macroscopic polarization of water next to surfaces and using that to characterize hydrophobicity and hydrophilicity. And the idea is that if you look at charge densities that come out of electrodynamic simulations on the atomic scale, you'll get this thing with all this atomic detail. And it's very kind of difficult to see, what the consequences are going to be for macroscopic response. But if you add a coarse grain over molecular scales, you get something that looks much simpler to interpret and actually governs the macroscopic electrostatic behavior. And so next to a hydrophobic surface, which is the black curve, you get a dipole layer that forms from waters pointing their OH towards the surface. If I put a dipole going one way, you increase the polarization in that direction, which is the blue curve. Or if you flip the dipoles, you might flip the polarization and get that red curve. And we can look at integrals of the charge density to get a particular value of a potential difference. And this is what we use to quantify the changes in the network over many, many layers. And we started using this to look at things like patterned surfaces that people have looked at with density fluctuation techniques. And you get the same kind of picture. So our sort of electrostatic mapping can uncover a single hydrophilic site in a sea of hydrophobic things. You can have this asymmetry of hydrophilic does more to a hydrophobic than hydrophobic does to a hydrophilic. But then you can also look at patterns of polarization. So you can look at, let's say a hydrophobic surface and put a couple patches with the dipoles oriented one way and a patch with the dipoles oriented the other way. And you can look at these maps and you can distinguish not just that these sites are more hydrophilic than the hydrophobic surface, but you can actually distinguish sort of what kind of hydrophilic is it, right? So which way is it polarizing the water? And so you can see this polarizes the water one way and this polarizes it the other way. And an interesting thing here is that these patches actually polarize water in the opposite direction than if you had the entire surface coated with dipoles. And what happens here, if we look at the structure of the interface, is that if you have a uniformly dipolar surface, which is this red curve, the waters tend to sit into the grooves, and there's no sort of penalty for distorting the interface in this way because the waters can keep hydrogen bonding with each other. But if you look at the patched, the water density over the patches, it looks very similar to the water density of a hydrophobic surface. And this is because it doesn't want to distort the interface and disrupt the network near the hydrophobic surface. And you get, instead of it sitting inside the grooves of the surface, the waters sit on top and they polarize in the opposite direction. All right, we've used this to look not just at simple surfaces, but also assembly, right? So you could ask, why do we care if there's these different polarizations? And this is some work that's inspired by looking at hydration repulsion between membranes, which was originally done in the 70s and kind of reinvigorated by Roland Netz's group about a decade ago. And the idea here is that water can polarize at these different surfaces. I'll be done in a minute. And then at the midpoint, by symmetry, that polarization has to vanish. And so as you start to bring these surfaces together, that introduces an additional constraint. And so the free energy goes up and you get a repulsion due to this added constraint. And then you can develop a sort of a Landau theory for this, which connects to our mapping and uses a coarse grain polarization. The interesting thing, I think, is when you have asymmetric surfaces where water polarizes away from one surface and towards the other, this symmetry constraint doesn't exist anymore. And so you can get an attractive pressure between these two surfaces. And so we've looked at this for different surfaces like mica, where we have ion-specific effects that can change the collective polarization at the surface. If you have two mica surfaces coming together, they're always the symmetric case because it's the same surface and you get a repulsion. But then interesting things happen if you look at proteins coming on the surface, and I'm going to just skip through everything. But we have cases where sometimes this one side of the protein wants to bind to the surface. The ion-specific effect can flip the polarization at the mica surface, but not at the other surface. And so in some cases, you get a polarization-induced repulsion and a polarization-induced attraction in other cases. Right, and this actually switches on and off assembly of these things. So in the case where you're getting the binding correct, this is my last slide. You get things assembling in a liquid crystal form at the surface, which is what this protein was designed to do. This is a synthetic protein. It's kind of like you're just stacking Tetris. In the other case, the binding phase doesn't come down because these polarization-induced repulsions instead the other side does, and you get this sort of just jumbled mess at the surface that you didn't want to happen. With that, I'll leave up these messages and thank you.
A few questions, please. Yaroslav.
Oh, very interesting talk, thank you. If I understood correctly, so when you introduced this, in this case, like 3 hydrophilic patches, so the zone between these patches became more hydrophobic. So how do you think that would scale? So in this case, those patches, they were very close to each other. What if it would be like larger?
Yeah, so that's one thing we're trying to do is to look at how this scales. At some point, what's going to happen is that if that's dominating the surface, you may not have this competition between the hydrogen bond network over the hydrophobic rest of the surface and in this little area. But it could be that they just stay locally, but I think once you pattern the whole surface, it's probably going to go away. So I think this is really just a nanoscale effect. That's not going to have some macroscopic angle. So I don't think you can measure like a contact angle, for example.
Vasily, yes, please.
Thank you, Rick. Fascinating talk. I'm a bit confused about the mechanism. So I understood that if you have a hydrophilic or hydrophobic surface, you see the difference in orientation of those layers. But how it brings us to the different contact angle, I mean the microscopic surface tension. Can you comment?
The mechanism.
Yeah, how this orientation gives us the difference in the contact angle.
You're talking about in this case of the defects or something?
The possibility of is connected with the contact.
Yeah, so here we're saying that for these defect systems, we're saying that you can macroscopically, the contact angle is related to this free energy to empty volumes near the surface. Right? Then with this alumina surface, the point I was trying to make is that these macroscopic sort of relationships can break down at the nanoscale, and you can have things that, for example, are super hydrophilic, right, which would correspond to negative contact angles, right? So it doesn't make physical sense because there's other terms that come in at the nanoscale. But we can also take that and look at emptying volumes in these kind of configurations where there isn't even a macroscopic analog. And so it gets easier to empty these volumes between these things. And I think the reason why that it's easier to empty these volumes is because you sort of have these these bound waters that are oriented up want to form a hydrogen bond network with waters oriented one way. But the rest of the waters over the hydrophobic surface want to form a hydrogen bond network with waters pointing the other way. So there's sort of this incommensurate networks that have to adapt in the region between the vacancies. And this is something we're working on, trying to find a good way and a clear way to characterize this, but it's something that we're trying to figure out.
Simone, yes, please.
I think I had kind of an extension of the question you was asking. So my understanding of hydrophilicity and hydrophobicity is essentially that you're asking whether a water molecule is better to stay close to the surface or in the bulk. Okay, so in your case, when you have these kind of hydrophobic patches produced by hydrophilic spots, is because when you have molecule around there, they can overall form less hydrogen bonding than in the bulk. So if you take a water molecule in the bulk has 4 hydrogen bonding, if you take it there, while those around the hydrophilic patches, they are nice, the other one cannot form a complete hydrogen bonding with 4 hydrogen bonds. So it's essentially this what you are saying.
Yeah, or the hydrogen bonds they're forming are less good.
Yeah. So you have some kind of strain or some.
Yeah, some kind of strain on network.
Frustration.
Yeah, exactly. Frustration is probably a good way to put it. Yeah, exactly.
Peter?
Yeah, very nice talk. Thanks very much. I had a question probably on this slide. So you seem to suggest that this assembly of proteins works exactly like this vacancy type of it's, well, the same mechanism that Nolan was talking about. The effect that you have patches of hydrophilic waters with hydrophobia surroundings. So is that something that also occurs in these proteins?
So I kind of went too quick through the protein. So the protein thing, basically what we're looking at is water is polarizing, to these different surfaces, the protein and the mica surface that's absorbing to. Neither of these things are really very hydrophobic, but it's the sort of the same idea that the hydrogen bonding network and sort of frustration in the polarization, let's say, can cause repulsion, or you can have sort of this additive thing where the polarization fields overlap and build up and it creates an interaction. Now, these are the forces that we think are significant at large distances. Once you start getting within, let's say, less than a nanometer, other effects take play, right? Like hydrogen bonding, and you can't use a continuum description of the solvent form. But I wouldn't say so much hydrophobicity in this case, but more this idea of polarization and orientation of water playing a role in the assessment. Yeah, let's talk.
Okay, so look, I think we should try to stick to the